In this screencast, we're going to look at vapor liquid-liquid equilibrium. This is a case where we have two liquids that do not mix, which means if the liquid is present, it's going to exert its vapor pressure independent of the other liquid because the liquids are in separate phases. What we're showing here is a temperature versus mole fraction diagram for two immiscible liquids. First, I should point out that these extensions don't exist. These are here just to show you the behavior. In the orange region, we have two immiscible liquids present, no vapor, and of course a large region where vapor. But this region, the vapor has two components, and the liquid has just one. So it has pure liquid 2 in equilibrium with both species in the vapor phase. And the pressure of component 1 is below its saturation value, and therefore it does not condense. Likewise, this smaller region over here, two components in the vapor phase in equilibrium with pure component 1. So a point here, for example, consists of pure component 2 and a vapor with both components 1 and 2. So we have four possible phase arrangements. And if we were to look at behavior in this system, if we were to start here and lower the temperature, when we got to this temperature, just one component would condense out. Component 2 would condense out because we reached its saturation pressure. As we continue to lower the temperature, we would end up with pure component 2 and a vapor phase that is enriched in component 1 compared to the original vapor. Keep in mind the partial pressure of component 2 is its saturation pressure in this entire region. Just like in this region on the right, the partial pressure of component 1 is its saturation pressure. And we have one composition that corresponds to a mole fraction of component 1 about 0.72. If we're to start in the vapor phase, as we lower the temperature, we get to this point where now both liquids condense. So this is the only condition for this pressure where both liquids and vapor are in equilibrium. And this is because the saturation pressure of component 1 plus the saturation pressure of component 2 at this temperature equals the total pressure, which in this case 180 kilopascals. Now if we go back and look at the point over here where we lowered the temperature, as we continue to lower the temperature, we get more and more liquid 2, and the vapor gets more and more enriched in component 1 until we get to about 112 degrees. And now both liquids start condensing because once we get below 112, we have just two liquids. This point corresponds to so much of liquid 2, so much of liquid 1 in separate phases. So notice when we calculate the mole fraction of component 2, it's just the partial pressure over the total pressure, and the partial pressure, of course, is the saturation pressure because liquid 2 is present. We could look at the behavior from the other direction. Suppose we have two liquids. Suppose we're at this point 105 degrees, two immiscible liquids, no vapor. As we raise the temperature, we'll get to this point where now we have equilibrium between the two liquids and a gas phase. The gas phase contains both components, and the mole fraction in the gas phase is about 0.72. We would sit at this temperature as we continue to add heat to the system, and to all of of liquid 1 disappears. And so we're sitting at this temperature. Once all of liquid 1 disappears, as we continue to add energy, we move to this point. So this point represents pure liquid 2 and a vapor that is enriched in component 1. And as we continue to raise the temperature, more and more of liquid 2 evaporates, and so the mole fraction of the vapor increases in component 2 until we get to the point here where we're going to evaporate all the liquid and end up in the vapor phase. And so the thing to keep in mind when we're talking about immiscible liquids, if we have vapor present in equilibrium with the liquid exerts its own vapor pressure. It doesn't matter whether the second liquid is present or not, because they're immiscible. They're completely separate phases and behave independently.